This video tutorial is our starting point of our topic of vectors. Throughout the majority of our maths career so far, quantities that we've worked at is something that's called a scalar. A scalar is a quantity which can be completely described by a number known as magnitude. This is its size only. So for example, 12 oranges in a box, a distance of 20 miles, a temperature of a liquid, like 30 degrees Celsius, or a speed of 45 miles per hour. So this is what a scalar is. Noting generally in assessments you are asked to write as a sentence to describe what a scalar is and give an example. So we have to make sure you say it's a scalar as a quantity, which is described by only a number known as magnitude. But mix up the sentence, make it interesting for me to mark. Magnitude is all that's needed to completely describe a scalar quantity. So you can think of different ways to write that sentence. And then give me an example. 4 apples, 72 miles, 30 miles per hour, 10 degrees Fahrenheit. Could even be a force. 45 newtons. That is a magnitude. It's just got a value, a size to represent it. However, sometimes size alone is not enough to describe a quantity, such as directions to the nearest shop. For this, not only do you need to tell someone how far, that's the size, the magnitude, you also have to tell them a direction. When you have magnitude and direction, it's known as a vector. And for anyone that's watched the film Despicable Me, the little evil guy is called Vector, and he does say that he wants to cause destruction with great magnitude and direction. So he does explain what a vector is and why he calls himself that name. So a vector quantity is one which requires a direction as well as a magnitude in order to be fully described. So an example here, distance is a scalar, but displacement is a vector because you get the distance travelled, 50 miles, and a direction, west. A force of 3 kilonewtons acting at a 45-degree angle to the horizontal is a vector because it's got a magnitude and direction. Velocity is the vector, speed is the scalar, because a velocity has a speed, 25 miles per hour, that magnitude part, and direction, south-east. Again, in assessments, we like you to define what a vector is, so you have to be able to write a sentence. Again, this sentence is here, but it's good to mix up your wording of it. To describe a vector quantity, it needs both magnitude and direction. An example is a force of 50 newtons acting at 10 degrees vertical, or a velocity of 55 kilometers per hour north. Make sure it has both the magnitude and direction in the example for this. So let's go on to what we're doing with these magnitudes and the direction, so the vectors. A vector can actually be written in 3 ways. It can be named either using points at the end of a directed line segment. So looking at this diagram at the bottom, it goes from A to B. And the reason I know it goes from A to B is because on that line, the arrowhead is pointing from A to B. So that can be written either with a half arrowhead above it or a full arrowhead. They mean the same thing. It just depends on what software people are using or what they've written in their own career to date. Again, the arrowhead shows it starts at point A and ends at point B. However, the vector could also be written as a bold letter. So you'll notice here it's written with a bold U. It's a lowercase letter when it's written as just a single letter. So it's a lowercase, not capital. No, we can't write in bold. Okay, you could keep doing that over and over again. It's a bit messy and a bit time consuming. So by hand, we underline it, and that's how we know we're writing something as a vector. So when we're writing a vector with a single lowercase letter, you should underline it. That's 2 ways to name a vector. I said there's a third. The third is something that's called component form. And that's where a vector is represented by values written in a column. So this example here, 2, 3 is a vector in 2 dimensions. The first component of 2 represents an x value. So it's called an x component. You would move two values, 2 units, in the x direction. Whereas the 3 represents a y value. It's the y component, and it means you're moving 3 units up in the y direction. So if you wanted to plot that on a diagram starting from the origin, you'd go along the x-axis for 2, up the y-axis for 3, and you plot this point. This point itself isn't the vector. You must draw the line to connect the origin to the dot, and you really should have your arrow as well to show the direction of travel. That we started at the origin, went along for 2, and up for 3. So there's 3 ways that we can write a vector. We can either label it using letters. Make sure when you use the letters, you're going from the start to the end of the vector. So in other words, this one's flowing from D to C. Or you've got a vector written in bold, we write it as an underlined letter. Or you might get a line that tells you its components, I'm drawing my x and y axis roughly here, as 7, 2. So these are 3 ways that a vector can be written. Its start and end point is bold lowercase letter, or component form this is called. Now it's important in component form you realise that these values do not have a line between them. They are not fractions. At the moment I mentioned a 2-dimension one. You can have 3-dimension. It would be your x, y and z component. You'll find at this level of maths we concentrate mainly on 2 dimensions, x and y. So, what I said there. Suppose we have this vector r, and it's got an x component and a y component. If we plot it on a Cartesian diagram, that's your xy diagram, the graph, the axis, it would look like this. You would go from the origin, along for x, up for y, plot our point, and it's called r according to what I've written. This vector is subtended at an angle theta, this angle here, and it's measured anti-clockwise from the x-axis. So when we plot that point, xy, there's 2 things that's in highlighting. We have this value of r, and we have this angle. Now r is written there because it stands for the radius. If you imagine for a minute gravity didn't exist, and I pinned this little string here, and I flicked that ball, what shape would that create? Certainly I hope you figured it out from my Bitly could do an improvement diagram. It creates a circle, and the cross is the centre. So that's why it was given an r. R is for the radius. Theta is for your angle. The radius is your magnitude, and the angle is your direction. So that's your vector. A vector must have a magnitude and direction. So if we want to work out the magnitude, the value of r, there must be a way to do this. Let's use our previous maths knowledge. If we go back to that earlier vector, the one I gave you, which is an x component of 2 and a y component of 3, and it's plotted in this picture, 2 along, 3 up, you'll notice that I've added something in here down at this corner I'm about to approach. That's a triangle. What type of triangle is it? Right angled. We want to find the third length of a right angled triangle. What special Greek mathematician is going to help us? Pythagoras. Out of the radius of 2 and the 3, what's the longest side? It's the one across the right angle, it's the r. So to work out the radius squared, you square the x component and the y component, and then you'll take the square root of it. We can actually shorthand this a bit and straight away say that the radius is the square root of the x component squared add the y component squared. So that's the square root of 2 squared 4, add 3 squared 9, which gives us the square root of 13. And if we round that to 2 decimal places, 3.61. That's its length. So the length of that line is about 3.61 when we round. But that's not the full part of a vector. A vector doesn't only have magnitude, it also has direction and angle. So, can we use our previous maths knowledge to work out that angle? We've still got a right angle triangle. What part of maths do we use to find angles within right angle triangles? It's your SOHCAHTOA trig, where across in the right angle is your hypotenuse. Across from your acute marked angle is your opposite. The third side by default's adjacent. We've got number 3 beside O, so we tick the O. We've got number 2 beside A, so we tick the A. 2 ticks means tan wins. So tan of our angle is opposite over adjacent. That was the y component over the x component. To work out an angle, what do we do to move tan to the other side? We take the inverse of tan, that's the shift tan in our calculator, and it gives us the angle 56.31 degrees if we round to 2 decimal places. And this is the case for all our vectors. To work out the magnitude, we use a version of Pythagoras, and to work out the direction, the angle, we use the tan ratio. So, to work out a length, the magnitude of vector r, noting that it should normally be noted as the r underlined for a vector, with 2 vertical lines either side, that's how we write magnitude, although if you write r equals is accepted. So to find the magnitude, it's the square root of the x component squared, add the y component squared, and to determine the direction of the vector, the angle, theta is always equal to the inverse tan of the y component over the x component. These facts need to be memorised. Now, the bit I've wrote in brackets I'm going to explain in a minute. Remember to sketch the graph to determine the position of the vector. I'm going to explain that in a moment. In engineering, when you find the radius and you find the angle, it's usually written like this as polar form. So for our previous example that we did there, using our components 2 and 3, the radius was 3.61. We then use our angle symbol and then put the angle beside it, 56.31 degrees. That is writing it in polar form. Now, I said I was going to get back to this direction thing. We need to. When we're working in polar form, the reason it's so important to draw a small sketch of a diagram is because, unlike cast, when you solve trig equations, it doesn't go from 0 to 360. Instead, the angle is between positive and negative 180. For this, we still would normally start measuring from our x-axis. Everything up in this top half are positive angles, whereas everything on this bottom half are negative angles. That means this first part of the angle is acute because you've not yet reached 90 degrees. However, when you pass it, it now becomes an obtuse angle. Whereas underneath, again, we've not reached 90 degrees in the negative, so it's still negative acute. But from this point onwards, it becomes obtuse and negative. So, in other words, we have to memorise this diagram. It's either positive acute, positive obtuse, negative acute, negative obtuse. And I'm going to show you how we deal with this. So here's my first example. Find the magnitude and direction of vector v, which is x component of 2, y component of negative 1. So right now, this is a vector. To find the magnitude and direction, we're going to change it into what's called polar form. To find the radius, what do? We take the square root of the x component squared, add the y component squared, be careful that the y number being a negative should be in brackets. So that's the square root of 2 squared 4 plus negative 1 squared, which is 1, so it's the square root of 5. And if we round that to 2 decimal places, we'll get 2.24. So that's the length of our line. But we still need the direction. To work out the direction, it's the inverse tan of the y component over the x component. However, negatives should never be used when you're using the inverse of tan here. So in other words, you use the 1 over the 2. But before I put this in my calculator, I did say you should do a small sketch. So you absolutely need a small sketch. There's your x, there's your y. This vector goes 2 along in the x direction, 1 down in the y direction. That means your vector is down here. It's an acute angle, but it is a negative. So in our calculator, when we do inverse tan of 1 divided by 2, we get 26.57 degrees if we round. But that angle's positive, correct? All we do is turn it into a negative when we write it in polar form. So your radius goes first, with your angle going second, but we must remember to put a negative sign in. That's writing it in polar form. Here's another example. Find the magnitude and direction of this vector a to b minus 6, 1. So magnitude and direction is writing it in polar form. What sum are we going to do to find the radius? The square root of the x component squared, add the y component squared. Don't forget, negatives should be inside a bracket when being squared. Hopefully you know that negative 6 squared is 36. 1 squared is 1. It's why you're getting your root 37. Sticking to 2 decimal places, 6.08. But we still need our direction, our angle. To get the angle, it's the inverse tan of which component first in your fraction? Y over x, but don't use your negative. We need a sketch to work out if we are positive or negative, acute or obtuse. So a quick sketch here will tell us to go back for 6 in the x direction, up for 1 in the y. So our angle is positive and it's obtuse. So when we use our calculator to go shift tan of 1 divided by 6, we get 9.46 degrees. Is that obtuse? No, there's a reason for that. Trig is about triangles. So technically the angle we're working out is the one I'm shading in there. How do you think we get it obtuse? We take it away from 180, because that is your straight line angle 180. So to get it obtuse, we take the acute angle away from the 180, giving us 170.54 degrees. So finish it off, radius, angle, and then followed by the angle that's correct. Again, if it had been on the negative side, all we'd have to do is remember to put a negative symbol in when we get to our end. Now, what I'm going to tell you here is we can actually put this within our calculator, noting if I don't see working of how to find the radius and how to find the angle and written in full, we can't give you all the marks. But I would say once I show you this method, you'd be politely foolish to not check your answer. So in your calculator, above your plus button is the word POL for polar. Shift plus will get you polar. You want to enter your vector components. Negative 6 for the x. You do want to separate with a comma. Above the open bracket button is a comma. So it's shift, open bracket, 1. When you hit equals, your calculator is so quickly in the background doing both Pythagoras, inverse tan, and changing to obtuse, you'll see that you get R equals the 6.08 number. And if you arrow along to the right, you can see it knows to convert it to the 170 angle. So you can use that to check your answers. And another example here then, state the magnitude and direction for -4, 2. To find the radius, what sum are we doing? The square root of -4 squared plus 2 squared. Into our calculator again for the third time. Don't forget negatives should go in brackets. 2 root 5 is what it tells us. That is because it's 16 and 4, which is 20, so it can simplify it down for us. However, we want it decimalised. 4.47. To work out the angle, we take the inverse tan of what sum? 2/4, which is a half. You can simplify it down if you want. Don't use a negative. Instead, we need a sketch. If we draw a sketch, you go along for 2, but down for 4. Our angle is acute, but it's negative. In the calculator, shift tan, 2/4 or your half, 26.57. However, when we write it in polar form, we have to remember the angle is negative because that's what our diagram tells us. Noting, again, check your answer by typing in shift Paul, -4, 2 to confirm you are correct. Oh, bet you've told me I was drawing the wrong thing. Look at that. Good job I checked that to realise I drew my sketch absolutely mince. There's no other way to put that. Because what did I do stupidly? I did the y first. It said x is -4. Silly me. Back for 4, up for 2. That was a silly rookie mistake. However, it showed you how easy that is to do. X before y. So it should be positive and obtuse. In which case then, what sum do we have to do with the 26.57 to get it obtuse? Take it away from 180. Now, months gone by, I would have redid my video, but it's actually good for you to see we make mistakes as well. 153.47 degrees, and that was indeed what the calculator gave me when I did my check. So there's a good reason to do your check. If you make a mistake, you'll be able to spy it quickly. Apologies for that. Now, I'm going to make that the end of this video tutorial for now, just so you can let this sink in. So to find something into polar form, the magnitude and direction, to find the radius, it's the square root of the x component squared and the y component squared. To find the angle, it's the inverse tan of the y component over the x component. Do not use any negative signs here though. You need a sketch to determine if it's positive or negative angles, and acute or obtuse.